Okay, so Innopharma itself was founded in 2009. There are 3 divisions, one of which you'll be familiar with. The education side is also involved in upskilling. The technology division, we're here to enable advanced manufacturing using process analytical technology, and I'll give you some of the history there. But we have a 3rd division, technical services, and I understand that some of you have even come from there. So currently we have about 70 employees experienced in STEM fields, in pharma development, in manufacturing operations, and software development. And yeah, so like I said, we're based here in Sandyford, and under normal circumstances, of course, you'd be in the lab with us for a demonstration like this. Hopefully, we'll be able to see you by the end of your course. So, just to talk a little bit about the PAT, our journey so far toward advanced manufacturing platforms. We started, as I said, in 2009. Developing sensors focused on solids processing. So the ICON analyzer is a inline real-time image analysis tool that can be used for particle size detection. We have a 2nd generation of that device. We also have a near-infrared device we'll discuss briefly today as well. In fact, we'll discuss the 2nd generation of that too. We've been moving in the past few years, like everyone else, toward advanced manufacturing. So not just using the sensors and simple control mechanisms, but higher level control and automation, where we can use prediction and advanced analytics to tell us deeper information about our processes. And we've focused on the development of SmartX for fluid bed granulation and coating. That was how we started off, for crystallization, and now more recently for twin screw granulation. Okay, so there are some things that we've been working on that are of relevance to all of you, particularly around our research and development of industrial Internet of Things platforms for development and manufacturing. Yes, so I see PSD and NIR. PSD is particle size determination, and NIR is near infrared. So near infrared spectroscopy, it's one of the methods of spectroscopy that we'll use in the lab. And we'll look at that later on today. There will be a lot of acronyms and abbreviations. Please do ask if there's anything that I don't cover. Okay, so Industry 4.0, advanced manufacturing, smart factories, these are all buzzwords. And some of the buzz around it describes Industry 4.0 as a revolution. In some respects, though, it is just an evolution from Industry 1.0, the first industrial revolution, which involved mechanization, steam and water power. The second industrial revolution involved mass production and electricity. The third, electronics and IT systems and automation. The fourth is being described as cyber-physical systems. And most recently, people have started to discuss even Industry 5.0, in which we see how these cyber-physical systems interact with the environment. So there are questions of sustainability that have to be considered, and also the impact on people and culture and skills. So there is a 5th industrial revolution, at least being talked about at the moment. So you've taken this course at a very timely time. There is a regulatory perspective here as well. There's a good reason to start looking at digital transformation and advanced manufacturing, not least because it is being supported by the various Food and Drug Administrations, by the European Medicines Agency, and so on. They're really trying to push industry to include digital record keeping, and they're insisting that with standards and regulations, these things have to be controlled and monitored. And they're doing this by encouraging us with respect to how easy it makes manufacturing. At least that's what they claim. So, questions? I want you to spam the chat box now with some answers to these. What kinds of technology facilitate regulation in manufacturing? I just made the claim that the regulators want us to employ technology, process analytical technology, to aid in the regulation of manufacturing? What kinds of technology would help us to do that? What standards or regulations do you feel make it easier to comply with regulations due to technology? What technologies make it easier to comply with standards and regulations, or what standards or regulations are easier to comply with due to technology? Computer vision, I see, is one. Yeah, certainly. And in fact, our particle size analyzer uses automated image analysis. So related, deep learning, yes. So certainly artificial intelligence, machine learning, deep learning, yep, all of these things. And so I want you to think about today paperless records, APIs, sensors, yes, data integrity, absolutely. Yeah, so audit trails, yes. So here we go. Even these are exactly the right points. And these are in fact the arguments that the regulators are putting forward. It doesn't just mean that they have greater insight into our business. It means that we have greater insights into our own processes. Okay, what standards are only possible to comply with due to technology? You may have already given shared control, excellent as well. So sharing control across different sites, technology transfer, etc. Complete batch life cycle, yeah, exactly. Okay, so we understand. This is great. I'm delighted now you have actually engaged on this, and you have literally started spamming the chat box. But I'm going to have to turn away from that so I can concentrate on the rest of the presentation, because I do want to get to the tour as well. So some of the issues around advanced manufacturing, these things put forward by the regulator demonstrate, and our own experience in manufacturing shows us that we need that the need exists for more consistent, reproducible, and compliant executions of designs of experiments. So where we explore the phase space of process parameters and so on. We'll see more of that later on. Advanced manufacturing lends itself to addressing this need by providing workflows to facilitate this. Digitized quality by design approaches through automated design of experiment execution, but also, as you've pointed out, the automated collation, contextualization, visualization, and sharing of PAT and process data. So that's process analytical technology and process data, and bridging the gap between process engineering and automation engineering. So this enables faster process development. This means we can respond in real time, finding out how our process is doing, respond in real time to make changes in real time, and that way accelerate process development. And also, as mentioned, tech transfer. And of course, this enables manufacturers to take a more Industry 4.0 approach to quality by design and design of experiments. Okay, jumping on it a little bit too far there. So you've seen the automation pyramid, and what we're going to talk about today are essentially levels 0, level 1, and level 2, because we're talking about sensors and signals from the production process. That's the field. Those are the field sensors themselves. At level 1, using programmable logic controllers, for example, for the sensing itself and for manipulating the process, for controlling the process parameters. But we'll also talk about how we can get to the next level, the level of the SCADA and the human. So the level of the SCADA is the supervisory control and data acquisition, HMI, the human machine interface. And yes, this level is the level of monitoring and supervision, where we can compare, where we can compare. Yeah, this is not our invention, I should point out. This is the ISA 95 automation pyramid, but it's exactly that. The idea is that all of this data that we're collecting can be systematically joined together in a hierarchy from the sensor level, from the field level in our factories, right up to enterprise resource planning. And today, unfortunately, we're down in the weeds. We're going to talk about something that you'll need as digital transformation agents. Something that you'll need as digital transformation agents, which is an understanding and a grasp of how we get from sensors and signals to the monitoring and supervision level. Okay, so how do we get there? We get there by recording changes in our process using sensors, converting the sensor data into useful metrics, monitoring our processes in real time, determining ideal trends and limits, and then adjusting process parameters in response to those changes. All right. So before we move on, I want to pause here for a moment and ask if there are any questions. Do you have any questions on what we've covered so far? We're going to get to more exciting bits in a moment. All right, I see that at least one person is having trouble connecting there. No thanks with respect to questions. All right, well, perhaps we'll come back to them later on. That's better, okay. Okay, so I'll give you a brief introduction into crystallization in pharma. The purpose here is to give you some background to what you're going to see, the crystallization reaction that we're going to demonstrate later on. And in fact, is already being arranged at the moment. Everything is being set up for us here, so we can go through this. But I want to show you briefly some of the principles that we'll be covering today in crystallization. So just to move on with the slides. I beg your pardon. Especially to those present. So all right, crystallization. Crystallization starts when solute molecules in solution. I need to collapse my chat box here a little bit so that I can read the content. But yes, solute molecules are present in solution. They cluster together and form little units. And you can see this happening here in the video, which was the first direct video observation of nucleation happening in situ, and it was only achieved this year. It's very difficult to have microscopy that's this fine. The resolution that you're looking at is on the order of just a few atoms, obviously. So this is extremely high resolution microscopy, transmission electron microscopy. Here they've captured video footage of nucleation happening, and you can see crystals forming. These are crystals of salt, NaCl, sodium chloride. So what happens is clusters develop together. They form a critical size, a critical mass, and so this once they reach a critical mass, nucleation happens. These clusters start arranging themselves into regular arrays, and they prefer to arrange themselves in a specific way, the arrangement of least energy, and from that they form the first regular crystalline structures and grow from there. So these smaller units of clusters develop into crystal nuclei, and those nuclei band together to grow in a preferred direction. Now, sometimes the direction is not, it's not preferred, as in there's no energetic, energetic advantage to growing a specific direction. So the crystal grows in all directions. Is that like the tempering of chocolates? It's exactly like the tempering of chocolates. And there will be lots of talk of food in this, by the way, not just because we're following a recipe control method, but because many of the techniques that we use in chemistry, particularly crystal growth, are exactly the same techniques as we apply in the kitchen in recipes. So, in fact, a question time. There are no right angles in nature, which is common knowledge, even though it's patently false. You work for Cadbury's. We'll have to talk after this. Sorry. Yes. So examples of crystallization in everyday life. We've already had one. Thank you very much. I believe it was Susan. I missed the name. I think it was Susan who mentioned it. Chocolate. Was it Stephen? I beg your pardon. Okay. Yes, I want you to again spam the chat box, which I'll unfortunately have to open the chat box again. And yeah, I want you to consider what examples are there of crystallization or crystals in everyday life. And I'm going to give you some prompts here that will appear slowly. So as soon as I give you a prompt, I'd like, we already know one at least. Stephen Harford works for Cadbury's, yes. So Stephen has an example from work. Can you think of examples from home? Soap, very interesting, yes. And ice, excellent. Sugar, ice cubes, yes, excellent. In your food, so we've covered that. In nature, ice cubes, I guess, food and nature. Now, and on the island of Ireland, any takers? Ah, you got it. Nice, extra points to Armando. And in medicines. Does burning food count? Well, I suppose carbon could form crystal structure. Anyway, yes, you have the idea. Crystals are, in fact, all over what we're using. You're using a crystal right now to view this presentation. Any tablets? Interesting. Yes, tablets, whether in medicine or in electronics. Silicon chips are an example of an extremely refined crystal. Yeah. So what we're going to do is talk about the applications specific to pharma. Causeway. Yes. Sorry, there was a question mark over caseway, but yes, that we'll see that example in a moment. So the idea that there are no right angles in nature is patently false. Crystalline structures form, and they are atomically perfect crystalline structures, except where there are flaws. There are any inclusions. Anytime something else is included in the crystal structure, it causes the structure to distort from the perfect cubic. There are other examples of crystal shapes: tetragonal, orthorhombic, where one orientation is preferred, one crystal growth direction is preferred over another. Monoclinic, where the angles are slightly distorted. Triclinic, where multiple angles are slightly distorted from 90 degrees. And hexagonal, which are where the prominent angles are 60 degrees, or multiples of 60 degrees more or less. Okay. So yes, of course, salt being the most common, and you saw the formation of that salt crystal structure in situ. Okay. So what size ranges can crystals come in? Well, molten lava, when it's cooled, can form a particularly large causeway, a giant's causeway, no less. These are crystals of basalt that have formed in a hexagonal fashion, but extended in one direction, obviously. This happens with other crystals and at different length scales, different size scales. So there's a cave in Mexico, for example, that has particularly impressive selenite crystals, which are approximately 6 meters in length. But of course, Giant's Causeway is better. More familiar, the thing that people think of most when discussing crystals, diamonds, of course, on much smaller length scales, and then some of the crystals that we'll be talking about here on the order of 500 microns. But again, that video that I showed you, you were looking at crystals forming on the length scale of tens of nanometers. So much, much smaller again. Right, so these are used in the pharmaceutical industry, and they're used for good reason. These are in fact some nicely colored images of single crystals of various pharmaceutical compounds. And the reason that they're preferred in pharmacy is because in order to form a crystal, what we're doing is a method of synthesis that results in a very highly pure end product, assuming we can control it and do it correctly. So examples that we're going to discuss today and are very common in the pharmaceutical industry, and maybe this is what you were expecting to see in the discussion of crystals: glutamic acids, the alpha and beta form. That refers to this. It in fact refers to the molecular arrangements, the arrangement of atoms within the molecules. But what results in the difference in those arrangements is an entirely different structure, a different shape. So the alpha form has almost all equal proportions, whereas the beta form has a wildly preferred, very heavily preferred direction of growth. Yes. Similarly, what we'll look at today, piracetam forms 2 and 3 rather. There are other forms, but these ones, like with glutamic acid, form 2 has a more even growth. Has more even growth in every direction, whereas form 3 has preferred growth along one axis from one face, and that's purely down to the arrangement of atoms within the molecules which go to form the crystals. More familiar again, paracetamol. I think everyone is certainly familiar with that. So these compounds are synthesized as pure crystals before being crushed and blended and milled and all sorts of post-processing in order to make sure that these crystals are evenly distributed throughout the tablet, so that they can also be evenly distributed and or target specific parts of the body. Okay, so what is the driving force for crystallization? Through anyone who's dissolved sugar, and you brought up the example of sugar earlier, anyone who's dissolved sugar to make simple syrup for cocktails in this time of need is familiar with how it is easier to dissolve more and more sugar when you increase the temperature. So you can dissolve more and more and more and more sugar up to a point. If you exceed a specific point called a nucleation point, your sugar will start to fall out of solution. You can force this nucleation to happen by cooling the solution again, but sugar is very stable up to a great degree. But this is true of solutions in general. And in fact, what we're going to do here in the lab is to dissolve piracetam in isopropyl alcohol. So we're dissolving some medicine in alcohol, and we're dissolving it by increasing the temperature and then forcing it to nucleate, forcing it to start to form crystals by lowering the temperature. And we're going to lower the temperature slowly enough so that it forms regular crystals. So this factor, the driving force, is in fact the supersaturation ratio. And we'll discuss briefly how we can influence the supersaturation ratio. As you are familiar with in dissolving sugar, if you start off at lower temperature, you can see two lines here, two solubility lines, in fact. If you start at a lower temperature, you can't dissolve quite as much. You can't have such a high concentration. You can't have such a high concentration of sugar dissolved. But increasing the temperature allows you to dissolve more and more. And in fact, it's more and more the higher the temperature. But you'll notice that these lines are in fact moving together. And this is just a consequence of the fact that we can in fact oversaturate or supersaturate the solution. We can saturate it to the point where if we allow the solution to cool, the crystals will start to form and fall out of solution. So what happens then? In fact, there are other ways to induce this. If we're not careful, for example, even if it's extremely even if it's extremely high temperature, or say for example we've been very careful with everything with cleaning our instruments and so on, even a simple knock can cause something that's oversaturated to nucleate. So what we're going to do today is we're going to go to high temperature and just by lowering the temperature again with the same concentration, we're going to cause nucleation. At this point, this is the point at which the solution becomes entirely unstable. But you'll see that there's a gap between the solubility and the nucleation points in this experiment. Well, anywhere along that point, you can actually cause nucleation to happen. We're going to cause it today, like I said. Is there a convergence point? It depends on the solution. It depends on the what you've dissolved, and yes. So what do I mean by it depends on the solution? Well, for example, if in this case, if this is water, it's not. In fact, this is the solubility curve of paracetam in an alcohol. So at no point does this converge, because by the time you reach by the time you reach 70 degrees, your solvent starts to boil off. So theoretically, though, yes, and there are solvent solute compositions where you can, in fact, just by following the solubility curve, reach the nucleation point where it automatically nucleates. And in fact, there are some solutions that are so unstable that you can cause nucleation simply by scratching the glass. And in fact, if you've ever had a flat pint, sometimes it's because the glass is too new. There are no scratches on the glass, and no bubbles form. Bubbles are also a form of nucleation that can happen. Similarly here, what we're looking at in the center, this represents a highly supersaturated solution into which a seed is added that causes the rest of the solution to nucleate. Right? Once it starts to happen, it cascades. Similarly, this can happen. This can be triggered by anything that has a rough surface or anything that the solution molecules can interact with, like in the case of just sticking your hand into the reaction. We won't be doing that today, incidentally. Okay. So how do we generate supersaturation? We've discussed one of them already. What we'll do today is cooling. Can also be achieved by anti-solvent addition. That is where we essentially reduce the amount of solvent molecules that are available. We can do it via evaporation. So we slowly increase the concentration of the solution by getting rid of some of the solvent, or reactive addition. So in doing this, what we cause a crystal formation by including two chemicals that react together. Okay. So now at this point, I want to pause again and ask if there are any questions, because the next step is I want to take you on the tour of the lab. Are there any questions so far? Again, feel free to spam the chat box. All good. In fact, before we begin the tour, I might just give people the opportunity to have a bio break, if that's all right. So what we'll do is we'll just leave the slideshow up, and you can have a bio break, and we'll come back to this in 5 minutes. Near-infrared spectroscopy methods, although that's a slightly more mature technology. Okay, yeah. So as I mentioned earlier, the main control parameter here is temperature. So we're using a chiller to cool the experiment from starting at 50 degrees, bringing it down to approximately 5 degrees. Yes. All right. So also here in the lab, one of the instruments that we'll be using is a simple microscope. We want to show you some of the advantages, if only by showing you how time-consuming and laborious the processes, so the existing analytical technologies are, and we want to use that to demonstrate some of the advantages of using inline measurements. Okay, so what I'd like to do now is to show you some of what that microscope is seeing, and show you how those crystals look under the microscope. So what we have here is a sample that's been extracted. Oh yes, okay. So what we have here under the microscope is a sample that's been extracted from the process while it was at 50 degrees and just dropped onto a slide. even that process involves, even though doing that involves an operator extracting a sample, depositing it on a glass slide, and waiting for the solution to evaporate so that we can then view it under the microscope. That's a laborious process, and yes, there are easier methods. That's what people had to do, and what people still do in analytical labs. All right. So I want to switch to the screen now to show you what those crystals look like. This is what happened. This is what it looks like. This is what it looks like when crystals are allowed to form in an uncontrolled way. So the crystals cascade out of the solution at lots of different sizes and across different size lengths. This is not what we're looking for when it comes to pharmaceuticals. We want our crystals to have all of the same shape, all of the same size, and to be ultra pure. If I switch to another slide, here's one I prepared earlier. On this slide, you'll see the result of controlling the temperature, not just allowing it to cool rapidly to room temperature. This is what the samples look like when we deliberately monitor and control and slowly cool the solution over time. We can see there's very clearly defined crystals present. And so this is why we want to control our processes. It would be nice if we could control the processes in line, see just by looking at how they are, how the process is progressing in real time, rather than having to extract samples and prepare slides and so on. Okay. So again, I'm going to pause and see if there are any questions on what we've covered so far. So hopefully issues around, was everyone able to see that appropriately? Could you see the screen easily there? Could you see yeah, you could see the slides. Good. Okay. All right, I'll give you the chance to spam with questions. All clear, great. All right, delighted. Okay, so we'll move on. So what we've seen is the consequence of allowing the reaction to proceed in an uncontrolled way. And I hope that alone is enough to justify controlling the reaction, controlling things slowly. But what we would really need is a method, as I said, of looking into the process to see how it's happening and how it's progressing in real time. So for that, we need to look at the sensor data. So I'm going to switch back again to show you what the sensors are seeing at the moment. So we'll see what the Raman sensor is seeing, and we'll see what this is in fact what the Raman sensor is seeing, and it sees a spectrum. We have to process this data in order to interpret it. I'll talk in a moment, in a few minutes, about how to interpret this. But what we're seeing here is different wavelengths, or equivalently different wave numbers, and at each wave number we see an intensity. So on the y-axis here, this is intensity. It's a number of counts in the detector. So this is showing us the number of counts per wavelength or per wave number equivalently. Similarly, so this is a spectrum, and this is the basis of spectroscopy. Similarly, when we look at the FTIR, in fact, do it like this. When we look at the FTIR, we can see a lot of spectra taken over time. So this here, they are all overlaid. So this might be more familiar to you. Yes. And what we can do is, so we can process these spectra to see exactly regions of interest, how they're changing over time. But again, impossible to interpret this kind of data with the naked eye. These are the signals directly from the sensor. It's now refreshing. It's capturing more spectra, so it's going to overlay those again on one another, and we can again, as I mentioned, zoom in. But when it comes to processing the data to see what, when it comes to processing the data and interpreting it, we have to take a few extra steps. This is not as simple as just an image analysis method. So yes, is there a sampling rate? Sorry, there was a previous question. I'll come back to that. So really, inline is real time. It depends on what you're using. I think that's actually related to the sampling rate question. In fact, yeah, I guess you're following a train of thought here. Yeah. So many instruments, like opening the shutter in a camera, it takes a certain amount of time for the amount of light to hit the sensor. Yeah, and enough light to hit the sensor so that it depends on the sensitivity of the sensor, but yes, you leave you allow it to acquire for long enough to detect a strong enough signal. So that's what determines the sampling rate. In the case of Fourier transform infrared spectroscopy, it's quite fast. You can expect approximately one sample, one acquisition per second. So what we're seeing here is over 16 seconds, 16 samples are collected. There is some processing that has to be done. We'll cover that in a while, and so on. So capture, measure, release, and recycle in seconds, exactly. But in fact, what I should say is that this is the detection is happening just by delivering light and capturing the light. So rather than extracting a sample from the process and measuring it and returning it to the process, that's why we have our probes directly positioned into the process. So I'll show you again these probes here. This probe is seeing directly inside the process. It has fiber optic cables that are directed right into the reaction vessel itself. So light is delivered into and then collected from the solution. We'll talk about how that's converted so we get actual light signals from the solution as well there. But similarly, with our Raman spectroscopy instrument, laser light is being delivered to the solution and collected. Okay, so now it is possible to monitor the crystallization in time. It's possible to monitor the crystallization in real time, yes, and in general that's true. We have some steps, thank you, we have some steps to take to process the signal into something useful like concentration. But yes, it is possible to monitor, and we're already doing that. We're monitoring the crystallization, and we'll just do the extra work to convert that into concentrations. Is there a sampling rate? We've answered that. So capture, measure, and release, yes. If I understand it correctly, the technology uses inline sensors, no online or at-line. That is correct, although these instruments are capable, you can convert them to at-line or online. Now, the distinction there, just to focus, is there a lag time? Yes. So it is near real time. That's strictly correct. Now, so people talk about real time when and these terms inline, online, and at-line. Just to distinguish between those for a moment. Inline is where the instrument is within the reaction. It's within the process. Online is when a sample, automated or otherwise, is removed from the process for the sensor to detect against, and then returned to the process. So that's online. Whereas at-line is when it's physically removed, where a sample is physically removed from the process, and a sensor that is not attached to the process is used to measurement. So that's inline versus online and at-line. So that, yeah, and now Lisa's question, is there a possibility of the physical probe triggering more crystallization around the probe? Absolutely, yes. If it is a light probe, can it be done through the vessel? Yes, and we'll come to that demonstration later, particularly in the case of near-infrared. Other spectroscopy techniques are problematic in this regard, but near-infrared, for example, can be used to deliver light through glass and collect light again. And we'll have more detail on that in a moment. If it is a light probe, can it be done through the vessel? It's absolutely not a silly question. There are no silly questions. but that's a really interesting and challenging one. Yeah, the lag time, specifically with FTIR, because the signal is sensitive to changes in the presentation of the material, and it has a very narrow penetration, very narrow penetration depth. The signal is averaged over time. So, like I said, 16 scans are made and then averaged. The purpose of this is to eliminate any, to account for any noise, to average out any noise, but also to allow you to get a representative view of what's happening in the solution. And that results in a lag. And yes, it is a moving average. It is a moving average. Is there a lag? Cannot be truly real time. Now, other sensors such as the near infrared, or in fact, it is possible to use. In fact, strictly speaking, the spectrum from any of these techniques, because there is an acquisition phase, there's an acquisition time. That means that it's not real time. It's not real time. However, the use of chemometrics, the speed of acquisition is extremely fast in some of these detections. With near infrared, for example, you can get a detection on the order of 10 milliseconds, and so quite fast indeed. So very closely approximating real time. So the output signal requires to be characterized to be useful. Absolutely 100% correct. I'm glad you asked that question. We're going to talk about how that's achieved. Has sound been used to sense such processes? Yes, and in fact, some of the more advanced techniques involve entirely other parts of the electromagnetic spectrum, but sound itself, so it's still in the research phases, but sound is used, for example, in the detection of faults. But the same analytical techniques that are used to process optical signals can be used to process audio signals. In fact, Fourier transform is a mathematical process that's applied more often in sound than it is to light. So, have I missed one? When you say average, moving average, it is a moving average in the case of this. Any experience with sensor jabber? Yes, absolutely. And in fact, some sensors have to be designed around using multiplexing to account for sensor jabber. But yeah, luckily none of the sensors that we have in-house at the moment have that problem. I'm drawing a veil there, but that's because in my experience in other industries, the trend is more important than the accuracy. Yes. Is that the case for the Raman technology, or is accuracy the key parameter? Okay, so yes. So there is even an application of NIR, for example, analysis of blend or content uniformity, where the only important factor is the trend. And COVID numbers. Okay. All right. Thank you. Yeah. All right. So not long as well. Thanks. We're experiencing technical difficulties. No. Good. Oh yeah. Okay. Very good. Well, so some sensors can be used to monitor blend or content uniformities. That's the degree of the mixture, and obviously in pharmaceutical manufacturing, as well as in food and other sectors, other types of manufacturing, it's important to have a uniform mixture. It's important so that you have even distribution of your pharmaceutical ingredient within the tablet. It's important in food so that you have an even distribution of flavor in your cornflakes, etc. So when we're monitoring this, we could start monitoring all of the different concentrations of all of the elements present, or we could just keep monitoring until changes slow down and stop. Another example is the fermentation in beer or cider production. The trend is more important than the accuracy of the degree of fermentation. Yeah, absolutely. And exactly the same, and for exactly the same reasons, monitoring blend uniformity or content uniformity, which is where we analyze the distribution of an active pharmaceutical ingredient within a tablet. We're interested in mixing until it's well mixed, until it's homogeneous. And obviously, if the signal changes in response to changes in the concentration of what's present, when the changes slow down and when it stops changing, it means our mixture is well blended. Okay, so the trend there is more important than the final values. But for some processes, and particularly for processes where you need to know that you've processed to a specific concentration, the only way is to use chemometrics with your process and analytical technology, where you convert the signal into concentration or other information. Okay, so I want to take you now through some of the details on the process analytical technology. I realize you've been very engaged with the questions. It's been fantastic. Please continue. If you have any more questions, you can continue to ask them. I'm going to switch over to the presentation now again, so we'll continue from there. Okay, so we're going to talk about the process analytical technology that you've seen so far today. So we've been using this obviously to monitor crystallization reaction, in which there are process parameters that we can change. So there's the cooling rate, there's the initial temperature, there's the initial supersaturation, because we can continue to dissolve more and more as long as the nucleation isn't encouraged. We can in fact start the nucleation process in the middle of the supersaturation region that we discussed. We can start it by introducing a seed on which the reaction can start to nucleate, or we can change the seed amount or even the seed location. And yeah, of course, we can control the agitation speed as well, the rate at which it's stirred. So those are the parameters that affect nucleation and growth. I also want to discuss the critical quality attributes. So if we look at this, we're forming a pharmaceutical ingredient. We're synthesizing a pharmaceutical ingredient here. So we have to consider the attributes, the qualities, the quality attributes of the end product in this process. And the critical quality attributes, the things that determine how good our end product is, those are crystal size distribution, the purity of the crystal, desired polymorph, and yield. Now, polymorph may be unfamiliar with those without a background in chemistry, but in fact, so a polymorph is simply a different crystalline arrangement, by which I mean the difference between soot, which is carbon, and diamond, which is also carbon. And exciting things like graphene, less exciting things like graphite in the lead of your pencil. Those are all just carbon crystals. In the case of soot, it's amorphous, but different arrangements of carbon atoms, those are essentially different polymorphs. Today, in our experiment, we have, as I mentioned, we're using piracetam, which has the two different forms, two different presentations that result in different shapes of crystals. So we can distinguish between the polymorphs that are present. Okay, so those are the critical quality attributes, the things that define how good an end product we have. And we can use our PAT to monitor these. Before we get there, I want to prompt you to relate back to me. I want to see if you can guess, based on the critical quality attributes, what are the challenges in crystallization? And again, I want you to spam the chat box, and I'll monitor it to see if there are any exciting developments. But you've already hit on a lot of this in the questions that you've been asking. Getting my wild whiskey with the right consistency and sweetness, absolutely. Okay, well, I'll prompt you. Whiskey and chocolate in the right class. Well, I mean, who wouldn't want to be in the class about whiskey and chocolate? If only there were some magical way of combining the two. Determining the correct range of the process parameters. Yeah, exactly. Okay, perfect. All right. So challenges here: yield, purity, undesired forms, size distribution. So size distribution refers to uneven distribution. If the crystals grow too large and your stir speed is too high, that can cause crystal breakage. Controlling the crystal size, and so even after the crystals have nicely formed, they can still agglomerate. But all of these things can be controlled by controlling our process parameters. But to get there, we have to be able to see what's happening in the moment. The example of crystal breakage is a good one. If our crystals grow too large, they can break off each other. You'll also see this in oral solid dose manufacturing, which you'll see in another demonstration, another virtual tour. Breakage of granulates. We want to form granulates of a desired size, but if you dry the material too much, the granules become too fragile and brittle and break off one another. Okay, so we can use our process parameters as long as we're getting decent signal. A question? So yeah, several reasons for an uneven distribution. One of the examples that we looked at earlier with the slide where the crystals were allowed to just fall out of form rapidly, cooling in air, you get a crystallization that's not homogeneous. Small crystals form as well as large crystals. So the smaller crystals can clump together to form agglomerates, but when the speed of crystallization, when the speed of nucleation isn't controlled, what results is an uneven distribution of end product through agglomeration and through different forms being present. The freezing of boiling water is via an ideal crystal process. So I think this was in reference to videos circulating around the internet where you can take boiling water. This is actually probably more true of just where you take boiled water too. I mean that it is quicker. Yes. Okay. So yes, it is freeze, and there's good reason for that. What's happening in that case is that because there is so much energy in the suspension, when it's rapidly cooled, there are far more nucleation sites. So yes, it freezes. It freezes much more rapidly when you're starting from. But this is something that can only be believed by seeing the demonstration. And unfortunately, that is not something I'm going to demonstrate in the lab today. But it is something that you can look for yourself on YouTube. I believe it was in Siberia. There were extreme temperatures, freezing temperatures, where people went outside with boiling water and threw it into the air. As they threw the boiling water into the air, it froze while in midair into ice. So yes, there are so many possible nucleation sites because of the fact that the water is so energetic. That with so many nucleation sites, so many crystals form that soak up all of the energy, withdrawing the energy from the boiling water, bringing it to freezing immediately. So again, I know that needs to be seen to be believed. I didn't believe it myself until I saw it. My PhD was in crystal formation, so but yes, definitely worth a watch. Okay, so we know why we have to look at our process. We're going to talk about how to do it. Absorption spectroscopy is the simplest, so we'll start with that. It involves molecular vibrations. So different kinds of molecular vibrations correspond to different energies at a molecular level. What we're looking at here is a simple water molecule. And what you're seeing here is different ways in which the molecule can bend and stretch and move depending on its energy. So there's symmetric stretching, where hydrogen atoms pull away from the oxygen symmetrically, asymmetric stretching, rocking motions. Genuinely, the atoms can rock back and forth around the hydrogen atom. Scissoring, where they move together, wagging and twisting. Water is a very good molecule for demonstrations because it does all of these different kinds of molecular vibrations. At a molecular level, these things happen to water. So what happens when light hits a molecule like this? Well, it can be absorbed if the energy of the light is. I see that some of the text is off, hidden behind the graph here. I'll try to fix that later. But what happens is light can be absorbed when the energy of the light is the same as one of those vibrations. That means that we can use light to determine what's inside the process. We can determine what vibrations are present, and we can, from there, determine what molecules are, what atoms and molecules are causing that vibration or causing that absorption. So one of the ways to do this is to measure the output of your light source and disperse it using a grating. So this is where light is reflected off something white, and then the light that's reflected is spread out physically in space. It's dispersed. You can do this with a CD, and I'm sure you've produced you've seen the light reflected from a CD. You can see the rainbow distribution. So that's working as a dispersion grating because the lines are so close together. They're almost on the same size as the wavelength of the light. And what happens is that the light spreads out in space. So we see all of the constituent colors. So we can attach detectors to these. We can attach a detector to these so we can spread out the separate detectors, have a linear detector array to tell us how much light is hitting. So the intensity of the light that's hitting each element of the array, and that tells us the wavelength of the light as well as the intensity. So this tells us we can convert this into a spectrum, right, by collecting the intensity observed at each of the different wavelengths, at each of the different detectors. And from there, we produce a spectrum. This is of the perfectly reflective surface, and we can compare that to a sample. So by comparing light from a known reflectance standard to that of our unknown sample, we can measure the difference. And that tells us about what's present, what's absorbing in the sample. Okay. So in the case of water, in the near infrared, for example, what we would see are two absorption peaks. We see one absorption peak at around 1,450 nanometers, and another absorption peak at around 1,900 nanometers. So by shining near infrared light into a vessel containing water, we can see these two peaks. So we can determine if we have a solution, whether it's water or not. Water has peaks, like I mentioned, at 1450 and 1900. So alcohols, like whiskey, have a peak slightly higher in each case. Sorry, I seem to have lost my mouse. Oh, here it is. at each case slightly higher, and in fact has a double peak around 1900. So different molecules and the presence of different molecules can be detected using by just simply by looking at the peaks that are present or absent. In the case of hydrocarbons, for example, there are three peaks present in the near infrared region of space. So by a near infrared region, there's a spectrum of so there's the electromagnetic spectrum. These are a range of different wavelengths. Light is the light that we can see is a subset of this spectrum from about 400 nanometers to approximately 750 nanometers. Then there's the invisible light range, which we can feel, but we can't see. There is, in fact, invisible light at both ends of that spectrum, ultraviolet light that we have to protect ourselves against because it's damaging to skin. Infrared light that we can feel, we can feel heat being transferred through infrared light, and you can see it with an infrared camera. Then there's the infrared region can be broken up into sub-regions, and here the near infrared is the part of the spectrum that's near the visible part of the electromagnetic spectrum. When we talk about Fourier transform infrared spectroscopy, what we're discussing there is the mid-infrared region, but in fact it goes further again. Raman spectroscopy is also typically carried out in the region in the high visible range or low near infrared range. Okay, so light interacts with molecules by being absorbed. When that light is absorbed, we can detect by comparing light that's been exposed to a reflective material and a light that's been exposed to the sample. We can compare the two spectra to determine what was absorbed by that sample. So that tells us what molecules were present. Now, as I mentioned, and I thought I'd give you a close-up of the instruments and how they're inserted. So we have two probes that we're going to discuss for the crystallization reaction. There's an ATR FTIR probe and a Raman probe. So the Raman sensor, the Raman probe itself, is delivering laser light into the reaction vessel and collecting it again. The ATR FTIR probe is doing the same. In this case, ATR means attenuated total reflectance, and FTIR stands for Fourier transform infrared spectroscopy. I'll give you a brief description of what those are. In the case of Fourier transform infrared spectroscopy, we have an infrared light source. That's what was sitting out on the bench. And it's producing infrared light that's delivered into the sample. Now, things can happen when light is delivered to a sample. When it can be reflected, it can be absorbed, and the rest of the light that doesn't get absorbed is transmitted through. Other things can happen, but just for the purposes of this description, I think that's sufficient. What I've mentioned so far was absorption spectroscopy. Fourier transform infrared spectroscopy involves a particular kind of light. So this is infrared laser. An infrared laser is first used in the light source to generate an interference pattern, and that's what's used to illuminate the sample. Some of that light is then absorbed and some is transmitted due to the arrangement of the electrons and the absorptions by the molecule. And what is detected can then tell us two things. The peak position can tell us what molecules are present, the molecular structure, and the height and the area of the peaks can tell us the concentration. So we'll go into further detail in Fourier transform during the lecture that we'll have with you in, I think, week 7. But for the time being, that's the fundamental principle of how Fourier transform infrared spectroscopy works. But there was another part to this that I mentioned. The well, yes, and we'll only concern ourselves with absorptions and transmission today. But here, attenuated total reflectance is the other part. That's the part that allows FTIR, which is traditionally just a benchtop method. The attenuated total reflectance allows us to deliver the light into the reaction vessel and collect signal from the reaction fluid itself. Okay, so in this case, the infrared source is delivered, it's bounced back and forth, the light bounces back and forth. There's total reflectance inside a crystal, inside the reaction vessel, and the light is then collected by fiber optics, brought back to the detector. But again, a light that's reflected from the sample solvent molecules tells us what those solvent molecules are. So we use attenuated total reflectance, FTIR, to determine what things are still dissolved in the solution. But again, it produces a spectrum like we've seen. Raman spectroscopy, on the other hand, so in this case, laser light is scattered from molecules. Some of the light is scattered at shorter wavelengths, some at longer wavelengths. And it's just due to the molecules that are present and how much energy they have, their excitation states, what kinds of vibrations they're undergoing. Raman scattering, though, has much narrower peaks than the absorption spectroscopy that I mentioned earlier, the near infrared. And here, the shape tells us, the shape of the peaks tells us a lot more. Peak position tells us the molecular structure, like with FTIR. Peak height can tell us the concentration, but the peak shift can tell us the stresses within the crystal, and the peak width can tell us the degree of crystallinity or how amorphous the structure is. Okay, and again, we see that some of the text is hidden by the graph. But yes, so those are some of the parameters that we can monitor. So in the case peak shift, is this where we see many peaks? In fact, we have an example of peak shift right here. So, in this case, what we have are we've overlaid the spectrum, the Raman spectrum, from form 2 paracetam over form 3 paracetam. These are different polymorphs, and we saw that they had different crystal structure, but the molecular arrangement, the difference in the molecular arrangement can be detected using Raman, looking at how the peaks have changed from one form to the other. So that's what's referred to as peak shift here. So a shift in the position of the peak from one to another, or shift in the shape of the overall shape of the peak from one form to another. Okay. Any other questions at the moment? All right. So as I mentioned, the peaks that are present, peak position tells us what molecular structure, peak height, the concentration, peak shift tells us about the stresses in the crystal, and peak width, degree of crystallinity. The relative heights of the peaks. So this is from the top of the peaks to the troughs, or from the peak to the baseline. So the baseline can be a measure of signal from the crystal itself, but it can also be a signal from the solution. So the baseline is one of the things that we sometimes have to remove, because it can be attributed to the background, any stray light that's present. And you'll see that you saw earlier that the reaction is open to light from the laboratory, and our floodlights, for example, could even influence the experiment. But the background can also be due to the presence of an amorphous material. So, for example, I mentioned soot, but perhaps an easier thing well, a more familiar thing to discuss here is glass. when we compare glass to diamond, we know that glass is brittle, but in fact, absolutely. Sorry, I spotted a question there. Well, I'll come back to the question in just a moment, in fact. So, although I with a question around 5G and so on, I hope we're not getting into conspiracy theory territory here, but just in comparing glass to diamond, glass to what we call crystal is another example. Glass is in fact on when we look at the atomic arrangement of glass, although glass is very brittle and shatters into large shards, it is in fact amorphous. It's not, there are not crystals present, but the as distinct from crystal, as in crystal glassware, which in which crystals are present, and this is why we can when we look at signals through glass, we have to subtract the background, because it's got a signal that does not have any peaks to so we have to remove that from our process. We have to remove that from the scan. If we were to try and look at the same process through a crystal, we'd find that yes, essentially it is noise. It's signal at all wavelengths, perhaps not even to the same degree, to the same intensity, but it is that kind of background produced by amorphous materials being present. It is noise, and for that reason we have to remove it. Okay, so the other question that I skipped over and said I wanted to come back to: could high frequency signals, Bluetooth, 3G, 4G, and so on, also impact? Depending on depending on the wavelength range of your detector, absolutely. Those signals, those signals are electromagnetic signals, and they are in this. If you have a detector that's sensitive in those ranges, then it will absolutely interfere. Okay, interesting. Right, so what we're starting to see now in our experiment, we'll just switch back to the experiment very briefly. What we're starting to see already is that the solution has become cloudier. The solution has cooled now. We've been slowly cooling it, and at the moment it is at approximately 16 degrees. So what we're seeing here is the start of the nucleation, and that's causing the suspension to become cloudy. And in fact, it might, what we'll see later on is how this has an influence on the start of nucleation, how that has an influence on the prediction of the concentration. But to get there, what we'll do is continue now with, we'll allow the reaction to continue, and allow it to progress. That stir, there's an artifact just from the video capture that stir is spinning continuously. In fact, it's spinning at I think about 200 revolutions per minute. But just because of the way the video is capturing and the refresh rate of the video, it looks like it's stuttering, but it's not. It's moving smoothly. But yes, you can see there, even as I'm speaking, the solution is becoming cloudier and cloudier as more and more crystals form. Okay. So to continue with the presentation then, we're looking at today at crystallization of peracetam, and the solvent is isopropyl alcohol, IPA, an alcohol that's used for cleaning electronics and so on. And what you're seeing here is the solubility curve that I discussed earlier. Again, if you start off at 5 degrees Celsius, you can only dissolve in a stable solution. You can only dissolve approximately 5 grams per liter, 5 grams of peracetam per liter of alcohol. But at 50 degrees, in fact, I think we started really at 50 degrees, but we first started looking at the reaction when it was at 40 degrees. At 40 degrees, you can see that the amount that we can keep dissolved is much, much higher. It's in fact about 30 grams per liter, about six times more of piracetam can be dissolved at 40 degrees. So by cooling it back down, we're going to force, and we've already started to force this nucleation to happen because the solution has become now super saturated. Okay. The numbers, is this a linear regression? Well, this is a polynomial regression, and we will discuss linear regression with respect to comparing our we'll compare our reference data to our signal data, but this is just a polynomial expression that relates the solubility to the temperature. Okay. So yes, on chemometrics, I said it is applied statistics. And so for those of you who have no background in chemistry, this you might expect from the terminology used, you might expect this to be less relevant, but I can assure you this is a requirement of digital transformation technologies for any manufacturing process that uses process analytical technologies. Anything around spectroscopy, but even if you're not using spectroscopy in your process, you're still using exactly the same statistical methods to convert your data into usable process information. Chemometrics is just the easiest way of applying statistics and getting meaningful process data. But I want you to discuss something for me. I want you to take a few minutes as well to think about this. We might have another bio break while you're thinking about it. Correlation does not imply causation. This is common knowledge. When I put up common knowledge before about right angles, I provided counterexamples. No right angles, and yet, in fact, nature does have right angles in it. So it might be controversial to say that correlation does imply causation. Any takers? Why am I so confident that it does imply causation when there are examples like this? This is the per capita consumption of mozzarella cheese on the left versus the civil engineering doctorates that are awarded on the right. So clearly there's a correlation between the two. You can see that they track so closely together, there must be a correlation. This is what we mean by a correlation. Nope, I've missed one, have I? I must be overlaid. Okay, I'll retrieve the other after we have a bio break. But I want you to think about this. Despite the spurious correlation that I'm showing you here, I still claim that correlation does imply causation. So I want you to think about that during the bio break, and we'll come back to discuss it. I am so happy. Okay, great. All right, that's exactly the right answer. Correlation doesn't prove causation, but the info you get can lead you to further study because it does imply causation. Exactly right. 100%. I wish I could give out gold stars, chocolate bars, and whiskeys for that answer. I'm very happy. But yeah, we'll leave it there for the moment and take a 5-minute, a 10-minute. Yeah, okay. We'll give people 10 or 15 minutes, do you think? Yeah. Well, all right, we'll go for full 15 minutes. You'll give yourself a gold star. All right, I'll see if I can arrange a virtual gold star as well in the meantime. So yes, take 15 minutes, please, and that'll bring us back for, let me see, 10 to. Yeah, so that'll bring us back 10 to 12. All right, I'll leave this presentation up, this part of the presentation up for the time being. Okay, thanks, Chris. Welcome back, everyone. I hope you could see that the reaction was progressing there, and in fact, I found the other correlation here. Apparently, the total revenue generated by arcades correlates very well with computer science doctorates awarded in the US. So I think here there is an implied correlation, but as well. So can we prove that the two things are connected? No, we can't. That is not what correlation does. It just implies correlation. It doesn't prove it. Exactly as Deirdre said. And I hope you saw your gold star there, Deirdre. Okay. Oh, there we are. Okay. Excellent. All right. So before I move on, are there any other questions? Are there any questions about the topics that I've covered so far? You're very welcome, Deirdre. You deserve it. Okay, so if there are no other questions, feel free to pop it, to ask your questions. Okay, great. Glad to hear it. Glad to hear it. Okay, so correlation. What does it mean? Well, on the left, you can see an example of strong positive correlation. On the right, you can see an example of weak positive correlation. So correlation is when we compare two sets of data, two variables against one another. A positive correlation is when when the data tells us that when one grows, so does the other, or at least that they seem to grow together. Correlation implies causation, but like we said, does not prove it. On the left, it is strong positive correlation because all of the data is clustered together around the trend line. A regression is done here to determine what the relationship is between all of the data. And on the left, what we see is that all of the data clusters around very close to this trend line. On the right, we see that the data follows the same direction, it follows the same relationship, but the data isn't clustered so tightly around the regression line, around the trend line. Okay. This can be described with a correlation coefficient, and there are multiple correlation coefficients. On the left, you see again our strongly correlated, strongly positively correlated data set. As we move toward the middle, that correlation becomes less and less strong until in the middle, it's impossible to see a correlation. That corresponds to a Pearson correlation coefficient of 0. On the left, with strongly positive correlation, that's a Pearson coefficient of 1, and on the right, negative one, where there is a very strong correlation, but as one increases, the other decreases. On the left, where one increases, the other increases too. Okay, so in order to resolve the correlation between things, and in order to translate that correlation, to use that correlation to go from signal to concentration, for example, what we do is we record the spectra at different concentrations. We measure our concentrations, so that's for our comparative data set. And we can prepare spectral data for that correlation. So if there's any processing that we have to do, and I'll discuss different processing. Yes, that was the Pearson correlation coefficient that I just mentioned. There are others. Spearman's, so R² is often used to correlate two data sets. That's the coefficient of determination. And they have different functions. We'll discuss some of those later on. But we record spectra at different concentrations in order to prepare a chemometric model. We can measure concentrations or use known concentrations for comparative data. We might have to prepare our spectra by removing a background, for example, or other spectral pretreatments. I'll take you through later in a moment. So then we calibrate, we do the correlation, we compare the spectral data and our reference data, our comparative data. final step, particularly for in GMP and in GMP environments, we have to validate the model that we produce against unknown concentrations, and then we verify that the model works in real time to achieve predictive accuracy that we need. So there's quite a few steps there to go from signal to useful prediction. But those steps go far beyond that. In fact, at step 4 there, we've already achieved what we want to. We've already developed our model. The rest is about validating. Okay. So background subtraction, we discussed it. This is how it can look. So when we record our spectrum, we might be looking through glass. So our initial spectrum is a combination of the signal from the sample and a signal from the glass. So we have to remove that, like we have to remove noise. And in fact, identical processing techniques are used to remove noise. Noise is removed in lots of different ways, depending on the spectroscopy method. Fourier transform is one of those transformation that's used to make noise reduction in particular easier. But in every case, it's a matter of subtracting the background spectrum from our signal to get the corrected spectrum. So this is a way of preparing our spectra. The other steps that we can take to prepare our spectra. Oh, in fact, let's just discuss what that gives us. So once we have these corrected spectra, we can use that raw, almost raw data in the case of one type of model development that we use here today. We can already use that near raw data just after the background is removed to do peak area analysis. As I mentioned earlier, peak area correlates very strongly to the concentration present. So peak height does as well. But peak area is a little bit more robust after background is subtracted. And I'll discuss that in just a moment. But yes, suffice it to say that what you're looking at here is in blue, the peak area versus over time throughout the cooling experiment. And in yellow, what you're seeing is the temperature as it's controlled by and measured by the chiller. And in fact, very briefly, I want to just show you what the chiller has been doing throughout this experiment, because we looked at it right at the beginning, but I want to show you the data that it was producing to show how it was being controlled. So I'm going to go back over here to where the Jullabo chiller is in action and has been throughout the process. So what we're seeing here, there are 3 different measurements coming from the chiller. One of them in red is the set point. So initially it was set at 50 degrees. Then it was changed to, this was all recipe driven. Sorry, I realize I've neglected to close my presentation so that we can see this. And for those of you on the web, I think now you can see a much better picture, I hope. Okay, so what we're looking at here in red, if I make this full screen, that will stop the clutter. You can see how this was controlled. This is recipe driven. This is recipe-driven control. I see. Sorry, I believe there was a problem with the audio, which I made worse. Okay, so yeah, what we're looking at here in red was the set point. Initially, the temperature of the chiller was set at 50 degrees. It was in the recipe, the next step was to go to 40 degrees, and then to slowly allow the temperature of the reaction to drop down to 5 degrees. So that was those were the steps in the process, and the steps in the recipe. We can actually see in blue, that's the temperature of the jacket. That's the fluid in the jacket around the reaction itself. So we can see how that responded to the changes in the set point. So initially it plummeted as the chiller cooled extremely rapidly to try to get to 40 degrees. The jacket temperature climbed back up, fluctuated around the set point before coming down in stages and so on to where it is now at 5 degrees. In green, what you see is that the actual temperature measured in the reaction with that probe that we looked at earlier. So you can see that In fact, it dipped slightly below 40 degrees, was held at 40 degrees for some time, and then followed with some lag. It followed behind the set temperature until it was brought down, overshooting a little bit, as these temperatures always do, before coming back up to 5 degrees. Okay, so this is, I'm going to switch back over now. I'm going to switch back over now to the presentation. So what we're showing here in yellow was the set point of the chiller over time. Interesting questions here, I understand. Let me see. I've been missing the questions as I was over at the. I need to expand this chat box. I'll go back up to the top. Okay, Pearson, yes, we were here. And so I assume all the sensors are using timestamp, yes, as key, and we are blending readings at the timestamp. Exactly right. How do we ensure that each device is on at the same time? So they, in fact, in this case, they're each controlled. The timestamps are controlled by the same device, but it is a question that challenges particularly older equipment that isn't, and it's one of the good justifications for connecting all of your devices to the internet. Cybersecurity issues and all to one side, but the point is, if you don't have something central that's applying a timestamp to each, yes, clock sync is a pain. Then you have to have some other method. Web synchronization is one of the methods employed. In our case, we've kept it very simple for the purpose of this experiment by running all of the equipment through the same sensor, through the same IPC, industrial PC. Okay. So yes, even something as simple as removing the background and focusing on one specific peak allowed us to map the changes in concentration. And that kind of simple analysis can be done as well using a type of regression known as principal component analysis. Now, I'll get into more detail on principal component analysis during the lecture. Suffice it to say for today that principal component analysis is a way of reducing the number of dimensions, reducing the complexity of the information to a simple form to do a simple kind of analysis like this. So I'll explain that in a little bit more detail now, and then further detail during the lecture. But before we get to that, I want to show you another way of preparing spectra called normalization and mean centering. So normalization might be familiar, but it's where, for example, the signal that's returned from inside your reaction or inside your process, if it changes due to, say, the penetration depth of your illumination, if it changes due to changes in vibration in the system, those kinds of changes are not actually, they don't actually correspond to changes in the concentration. So there are methods of adjusting the relative intensities so that they match up, and that's called normalization. It's one of the techniques in normalization. So this is another way of overlaying your spectra in a meaningful way, so that you eliminate fluctuations that are due to process changes that aren't of interest, and focusing only on those changes, like changes in concentration, that are of interest. So normalization, mean centering are very often used to prepare spectra, and as I mentioned earlier, dimension reduction. So what we do here is, well, the justification here, we can see on the left, our spectrum is a number of signals. In fact, for every detector, for every pixel in our detector, if we have a linear detector array, we have a separate signal. So we have a lot of data, we have a lot of things we could use to plot against our concentration, but not all of it might be relevant. It might only be some combinations of certain peaks that have to do with changes in our concentration. So principal component analysis tries to, principal component analysis and partial least squares regression, any kind of regression, the first step is involves reducing the number of dimensions, the number of variables, to only those which actually change with the change of interest. In our case, a change in concentration. Okay, so in the illustration shown, what you're looking at is a three-dimensional graph, and we can see that our what we've plotted it against three variables, but in fact, had we plotted it against these two components instead, so this small set of axes here, we would see that our data is much more spread out, and that the variations between them give us much more information about the real changes in the process. Okay, so what do we do then once we've got our once we've done our regression analysis, once we've compared known concentration or known attribute, critical quality? Have we got a question there? How many dimensions are typical that PCA reduces? How many PCA components would we reduce to 2 or 3? Okay, that's a good question, and it depends on, unfortunately, on the details of the data. So how many dimensions are typical that the PCA reduces? They can be in the thousands, and in fact, that's a good justification. And in the case of our Raman spectrometer, there are literally 1,024 separate signals. Principal component analysis tries to find some combination of the different changes in peak height on all of those. The light is an example. PCA tries to identify, principal component analysis tries to find what combinations of signals from all of those pixels changes most closely with the change in concentration. In fact, changes most dramatically over the course of the experiment. And it presents you with quite a few principal components. But how many should be reduced to 2 or 3? Well, so the principal components, what it's doing there is it tries to find, the analysis tries to find the ways in which your data is changing the most, and it then gives you, in order of highest priority, it gives you the components, the dimensions in which it changes the most, the components in which it changes the most. So, for example, your first component might correspond to 80% of all of the variation in your data set. Your second component might correspond to another 15%. So within the first two components, you've already got 95% of the variance in the data being explained. Okay, so I realize this is at a very high and abstract level. We'll provide you with concrete examples when we look at some of the data now in a moment. But yes, I think I see the next question. Unfortunately, my computer is frozen, so I can't read it. Oh, here we are. So we want to account for the majority of the variance. We want our principal component analysis to account for the majority of the variance, yes. And what the procedure is, then we identify which of the principal components, when they are ordered from most variance to least variance, actually track with the changes of interest. Like, for example, in the case of our experiment, our principal component, there is a change in like I mentioned, infrared heat. So that means that temperature affects an infrared signal. So it might be that the principal component, number one, the highest order principal component, that which changes the most with our experiment, is actually just one that would track the temperature. And only the second component tracks the second most important component, tracks with the concentration. So we have to analyze, we have to look at our data to see, to interpret, to apply interpretation. There are mathematical methods to do this by looking at scores and loadings. We can discuss that later as well. But yes, principal component analysis is used to account for the majority of the variance in your data, to separate out which of those variances are to do with process changes and which of those have to do with process changes of interest, process changes that relate to our critical quality attributes. Okay, so I intended that to be a much higher level discussion. Hadn't intended to get into it here, but very good question. Okay, so to get back to this, what we have in, say, partial least squares regression, where we're comparing, we're carrying out this regression, looking at the regression coefficients, comparing the known critical quality attribute to the predicted critical quality attribute. And if I recall correctly, this was an experiment looking at concentrations of salicylic acid in mixed in lactose. So aspirin in milk, in milk powder. No, very often lactose is a powder that's used in the pharmaceutical industry to disperse to disperse the active pharmaceutical ingredient. And acetyl salicylic acid is the active ingredient in aspirin. Okay, so when we can compare the predicted concentration to the known concentration, this can tell us quite a lot about, well, first of all, it can tell us about the data set that we used to make the calibration. But when we then, this means that we have built a model and we see how all of the data behaves. We see how much of the variance in the data is explained by the model. That's what the R squared tells us. So here it's telling us that 93%, 94% of the variance in the data is explained by that model. And another parameter that's reported here is a root mean squared error of cross-validation, and it's low. That's good. That means this model is performing well. But again, I'll get into the details of these parameters during the lecture. What we need to do in order to interpret how accurate this is we now need to apply this model to unknown variables, as we are doing today in the lab. So we have built a model, and we're going to use that model to look at how the experiment went throughout the course of the experiment, look at how the concentration changed. Here, what you're seeing is the result of doing this with partial least squares in the lab. We'll look at the result of doing it with principal component analysis, and those are by far the two most important regression techniques currently used. We'll discuss other regression techniques during the lecture. Here we can see that we did quite okay, that against our validation data set, where we repeated the experiment and used the model to make predictions in real time or near to real time throughout the course of the experiment. And we compared then, after it was finished, we compared the predicted values to the known values. And we ended up with an error of prediction of 0.32. Is the root mean squared error of cross-validation like the sum of errors on the residuals? It is, in fact, almost exactly that, except it's the root mean squared error of the sum of the errors on the residuals. So sorry, but yes, it's the root mean squared error. So that tells you how far away from the trend line each of those data points is. So rather than using the trend line, we can deduct the known values from the predicted values from the known values. So that gives us our residuals, as David mentions, right? So what's left over when we deduct the predicted value from the known value, and we can calculate the error on those residuals, which should be 0, right? If it was perfect, if it was a perfect prediction, it would match exactly the known values. But where there is an error, that means our model deviated from the ideal. and we can evaluate those errors with respect to one another, the degree of those errors, by looking at the distance between the zero line and those. That's why we take the root mean square of those errors. Okay, so rather than the sum, it's the root mean square. And again, how this works, we'll discuss in more detail. But before we move on, I want to pose another question with a lovely quote there from George E.P. Box. All models are wrong, but some are useful. What are some examples of useful and wrong models in everyday life? So again, feel free. I want you to spam the chat box. I'm going to give you some prompts so you can think about this and spam the chat box. Examples of useful and wrong models in everyday life. At work, in the home. Okay, wow. Okay, I'm pleasantly surprised. I lived in France, so all revenue linear models are useful, but usually wrong. Is there another? Oh, yeah. Oh, I lived in finance. I read it as I lived in France. Equally true. Incorrect KPIs being used to model the production line. Excellent. Okay. Yeah. Setting formats and templates, assuming they are a clear representation of performance or quality. Yeah, I can see the real need for digital transformation across multiple industries, judging from this chat box. Recipes designed for gas oven, and you have an electric. Perfect. Process flow charts, exactly right. Okay, excellent. I'm very happy with those answers. Okay. So, lost control over my presentation. Oh yes, on the island of Ireland or in medicines. Ditched out there for a moment. Okay, I want to move back to the lab now to look, if we're ready, in fact, to look at how chemometrics was actually applied in the real world, and to discuss prediction of yield. How we're going to predict the yield. Oh yes, thank you. All right. So, if I may, thanks. So, yeah, what I want us to look at is here. Well, before we look at the chemometrics next, well, what I want you to see here is how, for much of this FTIR spectrum, nothing significant changed. There were some fluctuations. Unfortunately, we've lost the overlay. But what you could see there perhaps was, and what you'll see building up here again, that for much of the experiment, there was no real change, only slight fluctuations across a lot of the wavelengths. But at certain peaks, you can see there is distinct activity, and these are the peaks that we would select on. And from these peaks, we would form our chemometric model. We would apply principal component analysis, and it would tell us that these are the peaks of interest, and it would, as I mentioned, show where the greatest variance was, and our principal component number 1 would probably track with temperature. So principal component 2 could be used for to apply the chemometric model to. While I'm waiting for Kieran to bring that up for us, we might discuss what's going to happen next, so that we can use this data, to make a prediction based on today's experiment. So what we can see now is that the solution has become fully clouded. What we're going to do, what Kieran is going to do in a few minutes, is to drain out the solution and all of the crystals present, transfer this into a filtration apparatus, and so pouring the solution into a filtration funnel with filtration paper in it. It's going to be drawn into the solution is going to be drawn into the vessel below using a vacuum pump, and perhaps you can see it more clearly now. Okay, yeah, I can see it on the live stream. Okay, so yes, the solution with the crystals in it are going to be poured into the filtration funnel with filtration paper inside. The solvent is going to be drawn down into the bottle, trapping the crystals in the filter paper. Yes, and the vacuum pump off to one side. And as long as we don't allow so much solution in that it gets up here, we'll keep our vacuum pump running. Okay, so what we'll then do is remove the filtration paper with our crystals trapped on the paper, and measure the weight of that. Measure, in fact, the mass, because we've weighed the paper in advance. We're going to weigh it afterwards, and we're going to then deduct one from the other to determine what mass of crystals we've produced. And we're going to compare that mass to the mass that's still in suspension, because having tracked the concentration throughout the experiment using the FTIR probe, we're going to see how much of the solvent is actually still present. It's applying one of these PCA, principal component analysis models. It'll tell us how much it expects after the temperature was dropped down from 40 degrees to 5 degrees. So yeah, once that's prepared, we'll take you through the comparison between the mass that we have actually extracted, the true yield from the experiment, to the theoretical yield from the calculated from the chemometric model. I'm going to switch back to the slides for the time being while we're waiting for Kieran to prepare the results of the model for us. And I'll need to start sharing my screen again. Okay. So some audio visual problems. All right. Okay. So what we've just discussed, the methods that we've talked about. We've have sensor attached to our process. I showed you a level 0 earlier in that pyramid. We've gone from level 0, the sensing of the actual process, to the control of those sensors and data acquisition, all the way up to level 2. This is something that you'll need to do as part of your, as a digital transformation agent. You'll need to understand the methods that are being employed to convert the process data through sensors into meaningful, so the process signals into meaningful process data. But what do we do when we get there? So it tells us the concentration. So it monitors over time. Well, we can use this. We can use this process analysis to ultimately control batches. We can use it for discrete control in the case of a programmable logic controller at the lowest level. We can use it for continuous control, where we have a continuous production process. But more valuable insights can be gained then once we have our control strategy implemented. More insights can be gained at a higher level when we start comparing process runs to historic runs, so that we can see not just how it is now, but how it compares to ideal trends and so on. Okay. Oh, hang on. Sorry, I believe I missed a question here. This is flow charts. Ah, I see. So alcohol is used for cleaning. So the transfer bottles will be washed with the same solvent? Yes. So in this case, the alcohol is the solvent of the reaction. Very frequently, IPA is used just for cleaning because it's a decent solvent, but in the case of electronics, because it's not conductive. So alcohol in this case is used for cleaning, not as the active pharmaceutical ingredient. The active pharmaceutical ingredient in this case is the paracetam. Yeah, very good, very good. In fact, I'm delighted our head of engineering intervened, because I was all on for eliminating entirely some of the manual steps involved in this process, not showing them at all. But we will. I'll have Chris show you as Kieran is actually extracting the solvent and transferring it for filtration and so on. Yeah, so we will actually show you these things, because as Chris rightly pointed out, some or many of you may not have been in a lab, analytical or otherwise, ever. So yes, I mean, there's more of a justification than just that. I think it is very valuable to see just how time consuming and how resource intensive these processes are, and if only to motivate you to start using fully automated inline and real-time or near real-time process analytical techniques. Okay, so now we're at a bit of a crossroads here, because Kieran has now prepared the data for us to look at. So what we'll do is we'll look at that data first, and then we'll let Kieran start emptying the reactor vessel and yeah, finding out what our yield was. So we'll make the prediction first, and then take a look at the yield. I'm going to switch from the presentation now. Okay. So what we're looking at here, yeah, so what we're looking at here, if you can see my screen, I have two windows open here on top of the others. What we're looking at here is a chemometrics software, is a piece of chemometrics software. This is Solo. There are many others available on the market. One that's very commonly used in industry, is Camo on Scrambler. Might be familiar to some of you. We have developed our own in-house chemometrics software specifically for near-infrared spectroscopy. But these tools are more general, and they're statistical analysis packages that can be used to interpret any two data sets. Or in fact, far more than just two. But you can build a model from any two data sets by comparing one to the other. So on the left here is the results of the principal component analysis. What we're looking at here is the residuals that were mentioned, and what we can see on the left actually it'll be probably difficult for you to see the details of the graphs. Unfortunately, that doesn't really zoom in on the graphs themselves, but suffice it to say that these are statistical measures of how well the component of interest tracks with concentration. What we can see is that at the start of the experiment, it measured approximately 35, in fact, we'll call it 34% concentration, and we can see that it dropped down to about 2 or 3% by the end of the experiment. So if that's correct, then what we should see is a change in the total concentration of 32% of the API. Another way to express to state that in a different way, what we're seeing is the result of crystals forming from suspension, and all we're seeing here is what's left after the majority of those crystals have formed and fallen out of the suspension. So the FTIR tracks only what still remains. Okay, so fell from about 34% down to about 2 or 3%. Yeah, so that's the prediction based on the principal component analysis. What I'd like to do now is to show you as Kieran is emptying the reaction vessel, transferring the fluid, the solvent. It's great to be filtered so that it can then be weighed, and we can give you the theoretical compared to the actual yield. So yeah, you can see that Kieran is emptying the reactor vessel. You can see the volume in the reactor vessel fall as he's filling his flask. And yeah. So at this stage, the reaction is at a steady 5 degrees. So it's been cooled past room temperature throughout the duration of the experiment. We can see maybe that there is still some. Yes, what we can see is that there are some crystals remaining at the bottom of the reaction vessel. What you'll be able to see, we'll point that out in a moment. Where you can see now the process of filtration. You can see that a lot of the crystals are actually precipitating out of the suspension because they can no longer stay dissolved. They're no longer stable. They fall out. They precipitate out. And so in order to get them out of the bottle, Kieran is going to have to swirl the bottle to transfer them as they're still suspended into the filtration paper. And you can also see there in the background that the reaction vessel itself has a coating of crystals too. When we get a glimpse of the background there, yeah. We can show you that again when Kieran is finished. Excellent, thanks, Chris. So, I mean, there's no way to mistake the fact that this is. There's no way to mistake the fact that this process is laborious and time intensive. Oh, questions? Or, as in the coefficient of correlation, the correlation coefficient? Oh yes, can or be used. I see. Sorry, I forgot the context. Yes, absolutely. And in fact, our in-house chemometric model development package uses OR. It's an open source. It's open source software that uses the OR statistical package for that. It's a very efficient way of finding your correlations. Okay, so you saw the solution being transferred. We could take more time, wash out the reaction vessel to transfer more of those crystals from the base of the reactor, but we want to use this as an approximate method. So we will give you a quick and dirty yield measure of the yield. Yeah, you can see. So thank you, Chris. You can see some of the crystals are still present at the bottom of the reaction vessel, but the point will be the same. So you were asking about the grade of the filter paper. It does have a certain grade. It has a specific mesh or filter size. Yes. Off the top of my head, I'm not sure what it is. Oh, good. So the filter papers are identified. In fact, different filter papers are in fact identified by the the effective pore size. Yes, so in this case, these Whatman filters have, oh, they're just identified by the number rather than the pore size. But oh, excellent. Thank you. Right. So this is what we're aiming for. These are the dried crystals from the previous experiment, one in which the previous experiment is one in which the model was built. And we can see that we have a very nice uh, distribution of crystals here. It's very uniform powder. Although I'm just saying this with the naked eye, we also saw that true using microscopy earlier. So we might even prepare a slide to look at from today's experiment so that we can look at that under the microscope too, to compare the results. Oh, yes, great. Yeah, thank you. All right. So while Kieran is going through the process of weighing, I'm going to take you through what we've discussed today, the methods that we've applied today, get us from the sensor and signal level to the level of monitoring for control. But what I want to talk about next is the steps toward control. And in fact, not just control, but as I mentioned, supervision, so that we can, where we're using the monitoring and control of the current experiment by comparing it to previous experiments, an ideal reaction or process development. So I want to switch back now to the presentation again. So if I share my slides one more time. Yep. We have in our own SmartX system, which is essentially takes people from the level of sensors, PAT, programmable logic controllers, and supervisory systems like a DCS or a SCADA, and attached peripherals. That means actuators and other process equipment that's used for control. The control methods at the next level, and visualizations, so that we can compare the current run to previous runs and to ideal batches. Yes, with that level of PAT, does that imply maintenance of long-term baselines for control purposes? Exactly. In fact, that's exactly where I was going next. The next level up is about manufacturing operations management. So yes, dispatching production, detailed production scheduling, with reliability assurance, generation of workflows, and so on. So that we have not just baselines, but we have trends and allowable upper and lower limits based on analysis in an analytical lab, a lot like this, even with other analytical techniques, where we just look at the quality of our end product and form, we form a picture of what a perfect process looks like by judging the quality of those end products using a full suite of analytical techniques. This means that we can develop, at this level, we can develop workflows that tie in not just with the quality of the end products, but that tie in with availability, with inventory, with stock management, and so on. So that brings us all the way up to enterprise level. Okay. So why bother? In fact, one moment, I'll just respond to a technical difficulty. All right. No. Thanks for the online support. No, the technical issue was relating to lunch. So, so apparently the people in the lab need to eat, and presumably that's the case of people at home. Um, but um, yeah, I want to pose the question here. Yeah, well, I want to pose the question first of all to see how people are how people are dealing with all of what they've received so far. Do they have any questions about the content covered? Because what we might do is just finish up this part of the presentation before we go for lunch, so so that we can ask Kieran then to make his measurements and give us the report on how well our prediction has performed. sorry, Warshak, I didn't mean to make you panic. Chocolate whiskey time. Okay, great. Porridge. Excellent. Okay. Well, and don't forget that the topics that are covered here today are covered in a series of lectures later on in the course, and it's not intended for us. You know, we're not. The outcome here is not that you will be chemometricians. We don't want that. That's not what we're expecting. What we want from this is that you'll be familiar with the techniques that are used to see into the process in real time, and to take the signals from the process to convert that into something usable. Okay, great. Okay. Okay, great. Yeah. So high level takeaways here. I think I'm still sharing the presentation. Yes, I see. High level takeaways here are that we can see inside a process. You've seen how it can be done. We've seen that we can convert that data, that sensor data signal into something useful, and then we can progress from there to monitor the performance of the reaction with respect to others. So we can monitor how well our process is performing against how it should. And then we can apply all sorts of interesting data analytics techniques, yes, for process insights, customized workflows, decision making, and so on. Okay, so we might break there for lunch. If you have any questions in the meantime, I understand that you get an hour and a half, but I feel like, judging what we have to cover, what we might do is keep it to 1 hour, and then come back after 1 hour. And I see the time is now, yeah, 1:45. So if we come back at 1:45, we'll do one final hour to wrap up. Yeah, so we'll break for lunch. I'll leave this slide up, I think, and as it summarizes a lot. And yeah, great. Guten Appetit, or buon appetito. Thanks, everyone. Hi, everyone. Welcome back. I hope everyone has enjoyed their lunch and is ready to go on. All right. So yeah. Oh, sorry about the delay in getting back to you. Okay, very good. I see that everyone is back in attendance. That's great. All right. So we will discuss, the higher level processing. But before we do, I want to take you back a step to where we were earlier, because what I want to do is to show you to show you our system, how after the model was applied. What I showed you earlier with the principal component analysis was the simple analysis on a peak area. With this, when it's applied to the entire spectrum, we get a slightly different picture. So there's something of interest to look at here. And we've arranged some of the statistics that we discussed that we can see in the model. We've arranged for some of these to be visible on the screen as well. So just to show you initially, this is what happens when the model is applied to the full spectrum. What we see is the progression, the change in concentration from approximately 31 grams per liter. I misquoted it earlier as a percentage. It's in fact grams per liter of piracetam in alcohol. What we saw is that the prediction of concentration drops from 31% all the way down to approximately 5%. With a spike probably due to our interference, the fact that we were, I think I was pointing out the sensor at this moment, which caused the sensor to shake. So yes, it caused a spike in the prediction. So one of the other things that I wanted to show you here was, in fact, the contributions from the different principal components. So what the principal components look like are different combinations. They're linear combinations of the different peaks and the different intensities, but they explain, the different components explain different amounts of the variance in the data set. So the first component explains 85% of the variance in the data. Second component, a further 5%. Third component, a further 5%. So after, so the combination of just the first three components results in 95% of the variance in the data being explained by the model. Well, I guess one of the bits that it left out, was its sensitivity to vibration. Okay, so but that's our final prediction. We expect a final mass to remain in suspension of approximately 5%. So I want to go back now to the slides. Or in fact, sorry, Kieran has already worked out, he's already done the measurement of the mass and so on. So we obtained, our yield was in fact 23.5 grams of the filtered crystals, which we showed you earlier, having started at 31.4 grams. So we could see that the concentration prediction agreed extremely well there. The final temperature being 5 degrees, and the solubility at 5 degrees being 5.7 grams. Our final concentration was approximately 5 grams. So yeah, and the calculated yield. So when we compare this 23.5 grams to what we expect to remain in the solution is in fact 25.6 grams. That means our yield was approximately 91%, with other losses being accounted for by what remains in the reaction vessel, as we saw. So very close indeed. But you saw exactly how laborious and arduous and time-consuming that process was. So I hope we've justified the requirement and the use case for process analytical technology, where you can measure these things in real time in the process, or near to real time, in line in the process. So what do we do from there? I'm going to start sharing my screen again. And yeah, we can take this process information, the concentration measurements, and we can compare it to where this process should be at a given point in time. But we do this via different levels of data analysis. So there's a data integration engine, for example, that allows us to carry out advanced dynamic process control, but also allows us to connect the sensors from the sensor level all the way through to cloud and edge deployment. So mobile apps, including mobile apps that are where the speed of connectivity is very important. That's edge deployment, cloud deployment, so that people can interact with our devices from anywhere in the world. But also, this allows us to have the higher levels of data processing required for higher level data analytics, applying machine learning and artificial intelligence, and more simpler functions, just like data visualization. The point being that we can use this data visualization and interpretation, and even automated interpretation, so that we have remote access, we can contextualize our data sets and analyze them automatically and in ways that are not human readable. Okay, so those are the ways in which we have to interact with the data and the advantages of the data of doing these things. All right. So yeah, today we've discussed how these sensor data, how these sensors can be attached to a crystallization process, and how the process parameters can be controlled via that process. We'll also discuss, you'll see this in other lectures and in other demonstrations, how it's applied to fluidized bed technology, for example, and you'll also have the opportunity to discuss this application with twin screw technology. You've in fact already identified amongst yourselves in the chat box the benefits of doing things in this way, in a fully integrated and connected way, sharing data and knowledge, collaborative research, cross-site process development and control. But yes, the real-time data visualization is really important for that automation pyramid, so that we can have enterprise-wide oversight on our processes and on multiple processes at the same time, for example. So we get all of the bells and whistles, not quite for free, but with a little bit of work. All right. So these are things that you'll have to be fully aware of as digital transformation agents. You'll have to understand the different parts of the platform that will be needed to connect from the sensor level up to the ERP level. And there are platforms available. The SmartX is one such platform that focuses on unit operations like twin screw or crystallization or fluid bed, develops the sensors and Internet of Things technology in a modular way to integrate the sensors with the process equipment, so that we can then use data analytic techniques through to achieve our third-party device integration with our cloud management and analytics system. Obviously, part of that platform means data security. So this is, whether you use the SmartX platform or any, cybersecurity is one of the pillars, one of the 9 pillars of Industry 4.0, as it will be of Industry 5.0. But yes, this integrated approach is what allows us to have automated design of experiments and workflows. Yes, so that means that we have to be entirely platform agnostic. So whether your device is from Thermo Fisher or from Wasatch Photonics, or whether your higher level data processing is done via Apache or Amazon or Microsoft Azure, our architecture is entirely independent. So there's a question here. Is there a preference for on-premise over in-premises over in-cloud? Well, yes, in different industries there are different preferences. So one of the ways, one of the arguments against moving to the cloud is, in fact, the lag time. So if your process is very, very time sensitive, it can be dangerous to only allow accessibility and control of that process via the cloud. Any drop in network connectivity might impede your process. Public internet being unreliable, for example, yes. So a compromise is in fact in edge deployment. So edge deployment is essentially connected devices that are locally implemented. So the idea being that higher level processing is and can be done in the cloud, but that the immediate control is managed on site and locally. So it's a combination of the two because it is a concern. So, I mean, are there further preferences for on-site versus via the cloud? Yes, certain industries are more reluctant on the basis that they view any connection to the cloud as being a greater risk. If you're aware of the recent attacks on power stations and so on, all cyber attacks that were brought about by directly attacking vulnerable parts of networks which have lower, much lower complexity than are, the things that we typically associate with being attacked by hackers. So when everything on your site can be connected to via the internet, that means that everything needs to be supervised and monitored for cybersecurity. So yes, there are industries that are particularly sensitive to on-premises versus cloud interactivity. Wait, did I miss another one? Okay, yes. All right, so in our case, we've developed this modular architecture that can interface via all of these systems to make it as robust and modular as possible. Let's see. Oh, yes. Okay. So we've discussed various control strategies, or I've mentioned various control strategies, recipe-driven control like this process. Other control strategies include endpoint control, feedback control, and dynamic process control. And there's also advanced dynamic process control, which we'll discuss next. But before we do, I'd like you to think of some examples. And again, I want you to spam the chat box. There are plenty of examples of all of these in the kitchen and around your house. So can you think of recipe-driven control strategies, endpoint control strategies, feedback control strategies, and dynamic process control strategies? Without the language is I'm sure familiar. There's not too much jargon in there. Central heating, perfect. Yes. Heating water, absolutely. Central heating is an example of which type? Thickening up my white sauce. Okay. Wow, we've already got the dynamic process control. Sorry, I'm giving the game away. Dishwasher recipe, perfect. Yes. Was this laundry? Oh my gosh, this is actually happening too fast to keep up with. I need a bot to do this for me. Oh, I see. No, the chat box has just jumped around. Heating the water, thinking of white sauce, dishwasher recipe and feedback. Yes. Washing machine, using the oven as feedback. Yes, absolutely. Air fryer, microwave use. So yes, my favorite example. Most of these are cooking eggs, right? So recipe-driven control. You know exactly what you're supposed to do in order to get a soft-boiled egg. You put it in the water for 3 minutes and you take it out, or 4 minutes, whatever. So that's recipe-driven control. But in fact, most people, when they're making an omelet, they use dynamic process control. So they realize that they're supposed to stir the eggs together, whisk the eggs together very quickly beforehand. They put them into the pan and allow the egg to roll around and form an even surface, and then fold and do all of that. But in fact, what most people realize is halfway through that they've made a mess of it, so they're going to use dynamic process control to change it into scrambled eggs. It's just genuinely an example of dynamic process control, with endpoint control being this, deciding, fine, I'll have them now, they're dry enough. That's scrambled eggs. Feedback control is adjusting, if you're a chef, adjusting the temperature at the right time so that it doesn't happen. All right. But yes, all of these strategies we're familiar with, and they're implemented all around us. But one that might be not quite so familiar is advanced dynamic process control and controller development, right? So this kind of development requires a deep understanding of the process itself. So we need to identify what our critical process parameters are, identify what the critical quality attributes are, and the quality target product profile. So what are we happy with? What should the end product look like, and how should it behave? That's what determines our critical quality attributes, and ultimately that's what helps us identify our critical process parameters. So we can manipulate the process parameters to explore the process design space, and we do this using ranging experimentation. So we start with a known good recipe, for example, and we identify reasonable upper and lower limits for a given process parameter. So if we know that a good starting point for the dissolution of paracetam is 50 degrees, we might start the experiment at 50 degrees, but in order to explore the space around that, we might have another attempt at the experiment where we start at 40 degrees and another attempt at 60 degrees, and compare the results of the end products. Or if we've already developed our chemometric models, we can monitor the process inline to see how it's evolving. And ultimately, we can use these kinds of ranging experiments to come up with dynamic process controls that can judge for themselves whether the product is currently moving in or out of spec. Okay, so the procedure that you then follow is mapped then to the right. So you can start with a model, you implement it, execute it, monitor, and optimize with real-time optimization, or as near as you can make it. Okay, to get there, of course, control logic has to be defined for each phase throughout the process. In our case, with the crystallization, this is one of the simplest demonstrations of how this might be implemented. We have the initial phase where the temperature is set. There's a set temperature of 40 degrees where it's maintained. In fact, the first phase is the dissolution. The second phase, is holding temperature, and the third phase is when nucleation is started by lowering the temperature at a specific rate. So in this case, we've already identified a recipe control, but to elevate that to a control logic that should be defined for each process phase, we could use the signal from our concentration measurements to judge how far out of spec the control is going. By which I mean, when we're exploring the phase space, if we see that our concentration, so we've started at a much lower temperature, if we see that our concentration isn't decreasing rapidly enough, it suggests that nucleation is happening too slowly. So we might end up with crystals that are too small for our purposes. But yes, so at each phase, we need to decide on a control logic. So that's to get from recipe to advanced dynamic process control. So yeah, we establish the key dynamic control relationships, fixed set points, phase and process endpoint criteria by judging the quality of our products. This can really only be done using real-time processes and PAT data. We need the constant feedback in order to determine where it is relative to where it should be. So we need flexible control logic to be implemented and executed via process-centric scripting. And again, a lot of motorized equipment, certainly. or certainly at least connected equipment. Yes, great. So yeah, our head of engineering, Chris, has just pointed out that he'll cover a lot of this in depth at the next demonstration in the process lab, in our oral solid dose manufacturing process lab as well. So there are specific implementations with other PAT, so with our particle sizer and with our near infrared instrument, and he'll discuss how we've implemented that for SmartX. Okay. So in the case of crystallization, though, this is how it can be applied for accelerated crystallization process design. We get our real-time process information, which gives us ultimately feedback control. So we can adjust process parameters on the fly, or have them, once we've set up the parameters, we can have them adjust automatically, which allows us to explore the phase space, the different permutations of process parameters much faster. So this allows for faster development. We don't need to wait until the end of the process to determine how it's performing, for example. So this is obviously quicker to implement as well. But here then, it's open standards, so it's easily integrated with and easy to integrate with. So as I mentioned, it's device agnostic. So the idea is that that this can be implemented depending on how the user already works. So it's user needs focused. And you'll see that this is the approach to take for all digital transformation solutions, right? So yeah, this is an example of how it needs to be done, because from one site to another, you might have different, even within a site, you might have differences in the technology, the PAT, or the process equipment that's used. You might have older stuff that needs to be retrofit. You might have newer stuff that already has a higher level, perhaps even the level of supervision. So these kinds of implementations need to be device agnostic and user needs focused. Device agnostic. Oh, yes. When you say device agnostic, I assume standard data connection methods between devices. Yeah, MQTT. Yeah. Or queuing and standard data layouts and messages. Yes, MQ or OPC. There are various open communication protocols that are used, and yes, standardized data layouts and everything. And in fact, when we talk about the journey from sort of pre-digital infancy to sort of advanced manufacturing, level 5 maturity, it is a journey of different layers of abstraction, different further layers of standardization and defined processes. So yes, exactly the description of going from the sensor level up to the ERP level, that is the same. It is the same journey. It is a series of steps of standardization, but also of open standards. Yes. So then yes, this system works because it's ready to go, secure. It's a secure cloud and edge solution. So there is standardized and automated data collection and data analysis. Have we got one there? Oh yeah, no, that's the same one. Okay. All right. So yes, what we looked at today was real-time integrated end-to-end solution. This the application of this technology at a higher level then is real-time integrated end-to-end solution for crystallization, process monitoring, and control. So it's a modular system that incorporates the different tools that we discussed today from different vendors using different communication protocols. MQTT on the part of the Raman spectrometer, and OPC on the part of the FTIR system. It's a modular system that incorporates advanced tools for process development and automation. So the SmartX system connects directly to our chiller for the control, or even the stirrer, and in fact allows a user to define recipes via the cloud, as well as on site. So, and delivers, as if I recall, Stephen asked earlier, it delivers time-aligned visualizations of the process machine and the sensor data, and even the interpreted data too. So it supports automating analysis workflows and ensuring data integrity throughout. Okay, so yeah, I'll switch back then from back into the lab. Oh yeah, of course. At this rate, I might not make it to those lectures that I mentioned. Yeah, so we've already discussed, in fact, the final yield. But what I wanted to show you was the results of our crystals. If I could have those crystals there from today's experiment. Yeah, I think they're still on the mass balance over there. Yeah, please. I wanted to show you the results of our experiments, our process run today. Yeah, so we have very fine grains, just as in the previous sample that I showed you. Oh, here we are. Hold it up. Just as in the previous sample that I showed you, very fine powder that has very good flowability. So why is it? Oh, here, I better help you out now. There we go. We can see the crystals twinkling in the light. Right. So yes, obviously one of the reasons that we want to be able to control the particle size, and this will come up in the next demonstration as well. One of the reasons that we want to control why it's critical is so that you have uniform distribution, not in the tablet for delivery, but also for absorption in the body. But even before you get there, it's critical to have flowable powders when you're processing them, adding your binders and so on. We need to have good control over particle size. So yes, this is how. This is the next step in the SmartX platform, is to include an imaging system so that we can actually see the crystals forming in real time. To a degree, if you go too small, then they compact too easily, which can cause them to clog equipment. It depends entirely on the crystal itself. Certain crystals are extremely flowable, regardless of how small they are, and they don't compact too easily. Some crystals are extremely problematic in that they refuse to compact, regardless of their size. But yes, there is an ideal size range, and there will always be a size distribution due to the nature of the synthesis, in that some of the crystals will grow to a certain size, then break against one another and become smaller. So you'll have a distribution of larger and smaller crystals present. Are there any other questions on the synthesis and the results today? Well, I think I'll let you think about that. So, does the distribution resemble a standard distribution? Frequently, yes. Sometimes it's a bimodal distribution. If, like in today's experiment, we had two different forms. We had two different forms of the crystals for during one part of the experiment. Because we left the crystals to grow, the less stable form after the crystals formed, the less stable form, form 2, essentially redissolved and were transformed into form 3 crystals. So, but in the initial, if we had looked at the particle size distribution, we would have seen two peaks: one for form form 2, which were the more rounded particles, and another size distribution for another peak in the size distribution for form 3. But otherwise, yes, it is a random, it's a stochastic process. So the result would be a normal or standard distribution. In this case, 2 forms were being synthesized at the same time, so we get a bimodal distribution. Another reason to get a bimodal distribution, and in fact, one of the graphs you pointed out earlier had 3 peaks in its distribution. The reason there being the presence of agglomerates. So yeah, an agglomerate can be when 2 crystals come together, could be when 3 crystals come together, and with a high enough resolution in your particle size distribution analysis, you can see those individual particles compared to multiples of those particles. So with 2 particles together and agglomerates where there are 3 particles, etc. Okay. So if there are no other questions, then I might wrap up. So you've seen how we've taken the sensor data. We looked into our reaction, and we took that sensor data and made sense of it using chemometrics. Part of that journey involved comparing the sensor signal just over time in the case of principal component analysis, and comparing that to how we know our concentration is changing. We also discussed how you can compare the signal to a reference method using, for example, partial least squares regression. And so we've talked about how to get from the sensors inside the process, seeing inside the process, to useful process information, and how you can then use that process information to evaluate the quality of your product in real time and make adjustments in real time, and at a higher level automate that process so that you can have advanced dynamic process control. So thank you very much for your attention. Thanks to Kieran and Chris and Wojtek as well. That was Chris. If you have any other questions in between now and the lecture, which I'll give in, I believe, weeks 8 and 9, by all means, feel free to send me an email. I'll put my email up on screen. Or after the lectures, you can ask in Moodle. If you do ask any questions, I won't identify you, but I will summarize the questions that I get and provide those questions and their answers to everyone, so that everyone has the benefit of those answers. Yes, slides will be available on Moodle. I'll set that up. And in fact, if you have any questions, feel free to ask me via Moodle as well. Once I am set up, I'll be circulating. Yes, I'll be circulating the links to the. Yeah. All right. Thank you very much.